Welcome everyone to chapter 2. So chapter 1 was like an introduction on derivatives. Chapter 2, we're going to start talking about graphs and what we can do with some derivatives. So by the end of this section, by the middle of this section, we're going to get into some pretty heavy application stuff. So strap yourselves in. It's pretty fun. I like it. So these first two videos today for 2.1 are kind of the same thing. In this video, this is going to be like an introduction with some like explanations. The second video is where the actual examples are going to go. So if you think these terms are kind of unfamiliar, sorry, I'm holding back a sneeze. If these terms are kind of unfamiliar, this is the video for you. If they're kind of familiar, then maybe just go on to the next video and see how you feel about doing the examples. So one of the things that this book talks about is these 6 categories for describing a graph. And that's what we're going to go over right now, what they are and kind of what they mean. The book has some very long, very precise, well, not very precise, but precise. They look precise. That's another thing. Definitions. If you really want to see the full out definitions, I'm just going to be kind of roughly explaining some concepts here. All right. But you can read the paragraphs in the book if you want. You don't need me to write paragraphs for you here though, I think. So here are kind of the 6 categories. So we'll go through them here. And again, if I'm going to quickly just list them all out. And if you think these are all obvious and you're good to go with them, then feel free to skip to the next video. Otherwise, we're going to talk about them in more depth throughout this one. So the first definition is when a function is increasing and decreasing, as well as minima, maxes and mins. So, roughly, it's increasing if it's going up, it's decreasing if it's going down. We'll talk about that. And a local max and a local min, sorry, these are relative or local. Max and min has to do with, are we at the top of a hill? That's a relative max. Are we at the bottom of a valley? That's a relative minimum. All right, we're also going to be talking about absolute. That's in parentheses because we sometimes say it, sometimes don't. Max and min values. So just like when we talked about average rate of change, and then we talked about instantaneous rate of change, a lot of times we left out the instantaneous part. And we just say average rate of change or rate of change for the instantaneous. This is similar, right? We'll say relative max or min. But if we leave out the absolute, we mean absolute even if we leave it out. All right, and that has to do with the absolute biggest and the absolute smallest the function ever goes. Next is concavity, which may be a new topic to a lot of you. Roughly speaking, concavity is, does it kind of look like an upward parabola? That's concave up. Or a downward parabola? That's concave down. And then we'll also talk about intercepts. So x-intercepts and y-intercepts. I think y'all are pretty good on that. Number 5 is where is it undefined? Pretty self-explanatory as well. And the last one is where are the asymptotes? The last 3 we can have a little review on, but I think it's the first 3 that are going to be the bulk of our new stuff. And I don't have the green screen on today, but I promise there's a 5 and a 6 right behind this green screen. And I'll try to remember that. So we'll introduce these some more. Here we go. Number 1, increasing and decreasing. So again, increasing and decreasing really is just as you go from left to right, is it going up or down? If you have this person walking, are they going uphill or are they going downhill? So it's increasing because they're going uphill. And if we add something like this, right, this is decreasing. Whoa, your arms are on backwards. All right, because they're going downhill. Going that way, he's going that way. So downhill means decreasing. And then again, kind of like I said before, local maxes and local mins are where there's a hill or a valley. All right. And specifically, let's look at this local max right here. So there's a relative or local max here. And there's a couple of things. We're looking at this point right here. At this very, very tiny point, this person is on flat ground. All right. Now, realistically, not really, but theoretically, at that specific point, they're on flat ground. We say this is neither increasing nor decreasing. All right, and that's what we mean by relative maximum, is the top of a hill. Now, it might not be the global maximum, but it is a relative maximum. It's the maximum around there. Just like if I go on top of White Mountain or something, that might be that's a terrible example. If I go on Pilot Butte, for example, I will be the highest around me. That's the highest in that area. But it's not the highest point in Wyoming. It's certainly not the highest point in the United States. And that's kind of what relative max means. And relative minimum will be the valley. Okay? So, yeah. This is to be contrasted with the absolute max value. And one more thing to talk about here is for this second thing, we talk about absolute maximum values. Whereas over here, these are points usually that we talk about. So it'll be like an X and a Y coordinate. Whereas for the values, it's just the value of the function. What's the biggest the function will ever become? All right. So let's look it over here and get some examples. So let's say we're looking at something like this. Let's say it starts here and it kind of goes up and down and then all the way up. So A, this is a local or a relative maximum. It's the top of a hill. This point B, that is a local or relative minimum. But B is also an absolute minimum value, or there's an absolute minimum here. So let's say the absolute minimum value is, I don't know, maybe that's like 1/2 or something like that. And it occurs when X is equal to 3. There's also a local or relative minimum or maximum up here. But there is no max value. It doesn't exist. And there's no absolute maximum value because notice this function just keeps on going up. It goes up forever. So whatever value, 5,000, 10,000, 20,000, this function gets bigger than that. So there is no maximum that it attains. It keeps getting bigger and bigger. All right. Next thing is number 3, concavity, which again, roughly speaking, is does it kind of look like a parabola that's going up or down? I can't really type and talk at the same time. I'm so out of it today. I'm trying to get these videos to you guys in time. All right, so in something here, oh, one more. I really am out of it. Another example that's worth talking about here for things to watch out for is that let's say if I have, say if we have some kind of bell curve like this, a very weird looking bell curve. This has an absolute maximum value here. The absolute max value is maybe 1.7 or something for this, but there is no minimum value because there's an asymptote. This function gets really close to 0 in both directions, but it never actually hits 0. All right, so there's no minimum value here. In this one, we'd say the max value is, I don't know, maybe 1.7, but there's no min value. And the minimum value is not 0 because it never hits 0. The minimum value is not 0.00001 because we get even smaller than that. So it's kind of a weird thing where we have to hit the minimum value for it to exist. Anyway, here we go. So concavity technically is how the slope changes. So again, just kind of roughly speaking, we can think about concavity as like parabola up, parabola down. This is a downwards parabola, so it should be concave down. But we can also think of it in terms of slope, okay? Look at the tangent lines at different places. Over here, this green tangent line is a pretty decently sized positive number. Over here, it's a small positive number. Over here, the slope is a negative number, and then an even more negative number. So the slope is decreasing. Oh my word. So that's another way of saying concave down. But again, if you want to think of it like a downwards parabola, go for it. Also, it really looks like I use that German letter here. I don't even know what it's called, but it's like a double S sound. Really looks like I'm trying to give one of those, but it's really supposed to be a P. All right. So again, some examples are, let's say that we have a cubic function, kind of like this. Well, this is going to be concave down over here, right? If I zoom in on this green section, it's like a downwards parabola. And it'll be concave up, kind of around there, where it looks like an upwards parabola. That's kind of the idea here. But again, it's how the slope is changing. All right, let's do some more definitions. So, we got one more attached to this one. What if I have this kind of cubic function? Over here on the left, right? This kind of looks like a downwards parabola. It's concave down. Over here on the right, concave up. But there's a point where it switches from concave down to concave up, and that's called a point of inflection. All right, so a point of inflection. Oh, that doesn't fit. A lot of times we'll abbreviate that POI, so it does fit, is where concavity changes. All right, and then again, x-intercepts, we know those. That'll be number 4. Remember, x-intercept is when y equals 0. And the y-intercept is when x is equal to 0. So a lot of times you just can find them from the graph, or you can plug in one of these 0 values and find what the x or y-intercept needs to be, right? Finally, not finally, one more. We got where is it undefined? And that can occur in 2 different ways, right? If I'm looking at some function like this, let's just say it's a line with a hole in it. This function's undefined at x equals 3. Right, it's undefined at that hole. But it can also appear with like asymptotes. Let's say I'm looking at this transformed squared reciprocal function. There's an asymptote at x equals 2, so we'd say undefined when x is equal to positive 2 as well. All right. All right, last thing to talk about is asymptotes. Asymptotes are equations of lines, so watch out for that. So again, just kind of steal from this one, there's an asymptote at this vertical line right here. Okay, so what's the equation of a vertical line? The equation of a vertical line is x is equal to 2. You can't just write 2, it needs to be an equation. Similarly, right? If I'm looking at an exponential function, like so, there's a horizontal asymptote on the x-axis right there. So the asymptote here would be the horizontal line, y equals 0. So remember to always include the actual equation. All right, so that's the just general description of what these categories are. You have them at the very beginning. So feel free to copy these down or just download them because I'll attach them to the videos and then use this to kind of guide your way as you're doing the examples that we will do in example 2.